Hi there, welcome to the Retro Desk. I'm Matt Heffernan. This is the second episode in my tutorial series for learning to program in 6.5 CO2 assembly language for the Commander X16. If you haven't seen the first video and are new to assembly programming for the 6502 family, or any kind of processor, I highly recommend going back to the first episode that lays out all the basics you need to know. This episode is going to be about addressing modes, which I touched on briefly before, and I am going to expand on what we started there. So please go back to my channel, and don't forget to subscribe, and check out that first episode if you aren't ready to get started here. Also, this is the second edition of the series, updated to work with the actual hardware. Before we get into the different addressing modes, let's take a look at the memory map of the Commander X16, and how that is handled by the 6.5 CO2. As with any 6502-based system, the X16 has a 16-bit address space, meaning that there are 64 kilobytes of directly addressable memory, with addresses from 0 to hex FFFF, or decimal 65,535. Those first 256 bytes, from 0 to hex 00FF, is the 0 page, which we discussed in the last episode, as the high byte of the address for that range is 0. The next page of memory, from hex 0100 to hex 01FF, is reserved for the stack, with the stack pointer register referring to the low byte of the address of the current top of the stack. As data is pushed to the stack pointer goes down, overflowing if it goes all the way down to 0, meaning the top of the stack is at hex 0100, and anything more is pushed to it. The 6502 does not support growing the stack into the 0 page. The next 6 pages, from hex 0200 to 07FF, are RAM reserved for use by the basic interpreter and kernel. Some data can be placed there by your program if you are extra careful. Generally, it is safe to use addresses in pages 4 through 7, as they are not used by default. This kilobyte is commonly called the golden RAM. The next 151 pages, from hex 0800 to hex 9EFF, is the basic program RAM, which is where we loaded our code in the previous episode. As we saw there was a single basic line making a syscall to start our machine code that started at hex 080D. That means we have a contiguous 38,643 bytes of RAM to grow our machine code program into. If we are programming in BASIC, the tokenized code would start at hex 0801 and could grow to 38,655 bytes. Sound familiar? That's what the X16 start screen says. The next page, from hex 9F00 to 9FFF, is not memory at all, but rather it is mapped to the input-output devices, like the Vera Video and Sound Chip and the VIA controllers. We'll get into how to use these addresses in a later video. Just be aware for now that we can't use any of that space for storing data. Then the next 32 pages, from hex A000 to hex BFFF, is the banked RAM window. This is where you can store up to 512 kilobytes of data across 64 banks of RAM. Optionally, an X16 can be populated with 256 banks of RAM for a total of 2 megabytes. We'll get into this in another episode as well. The last 64 pages, from hex C00 to hex FFFF, is the banked ROM, where stuff like the basic interpreter and the kernel machine code are stored, along with other data needed for running them. As it is read-only memory, we can't write any data there, but we can read and execute the data and code that is there, and we will need to when we get to calling the kernel functions. You guessed it, that's going to be another episode too. In the last episode, we talked about how instructions are formatted. In assembly language, you have the 3-letter instruction mnemonic followed by the operand. The syntax of that operand depends on the addressing mode you are using. Each instruction mnemonic translates to a set of opcodes, with the assembler choosing the one that matches the addressing mode of the operand after it. If the instruction doesn't support the addressing mode of the operand, the assembler will report an error. If you go to the GitHub repo for this tutorial that I linked in the description, you will find some links to references that show you which addressing modes are available for which instructions for the 6.5 CO2. In this episode, we will be going over each of those addressing modes and some of the instructions that they are used with. The first addressing mode we went over in the first episode was the immediate mode, which is denoted in assembly language with a hash symbol at the beginning of the operand. This means that a hard-coded value will be used for the operand rather than an address for where that data will be. As this mode can only be used for reading a value, it is only used by instructions that load data to registers, like LDA, or do some sort of arithmetic, or compare a value with the contents of a register. The next mode we used in our first program was the implied mode, which can be used for instructions that have only one opcode that needs no operand, or for instructions like inc that can be used without an operand to operate on the accumulator instead of a memory address. In both cases, the implied instructions only take up single bytes in memory for just their opcodes. The last mode we saw in our first program was the absolute mode, where a full 16-bit address is used as an operand. Rather than the value being hard-coded as in immediate mode, in absolute mode the address is hard-coded, while the data that is accessed may change. Absolute mode is also used for changing the flow of a program by jumping to a new address in the code rather than continuing to the next instruction by loading that address into the program counter. In assembly language, absolute mode is denoted by having just a simple 16-bit number as an operand. Unless that number is less than hex 100 or decimal 256, in which case you are specifying zero-page mode. This works the same as absolute mode, except that the address can fit in a single 8-bit operand. Most instructions that support absolute mode also support zero-page mode, but in the latter case it is more efficient. First, because the operand is only 1 byte instead of 2, taking up less memory as an instruction. Second, as it requires fewer cycles to read the instruction, it runs faster. This means that performance can be gained by keeping key values in the zero page for quick access when timing is critical. Very often, the actual address that your program needs to access is determined at runtime. You can't just hardcode the address when you write it. This is where the index registers X and Y come in. The values in those registers can be added to a base address at runtime to calculate the target address. There are 4 distinct addressing modes that are indexed in this fashion: absolute indexed with X, absolute indexed with Y, zero-page indexed with X, and zero-page indexed with Y. All 4 are used for multiple instructions, each using a unique opcode. In assembly language, this mode is denoted by appending a $X or $Y to an address, which can either be an absolute 16-bit address or an 8-bit zero-page address that is under hex 100 or decimal 256. In all cases, the 1 or 2 byte base address is the machine code operand, and the opcode will tell the processor how many bytes there are in the base address and which index register to add to it. These modes are commonly used in loops where you have to iterate over an array, or where you just have to access a single element in the array, and you load the index you are accessing into one of the index registers. Having both X and Y available means that you can maintain indexes in 2 arrays at once, which comes in handy when you are doing things like nested loops or copying blocks of data. If you have programmed at all in C, you are already familiar with the concept of a pointer to a pointer, which is used in the main function to present the command line arguments as an array of strings. In assembly, we can do a similar thing by having an operand that is an address of another address that is stored somewhere in memory. This is indirect addressing, which is 2 distinct modes for the 6502, absolute indirect and zero-page indirect. For this mode, it is assumed that a 16-bit address is stored somewhere in memory across 2 contiguous bytes. The address of the first byte of the stored address, and as this is the little endian 6502 we're talking about, this is the low byte of the address, is placed within parentheses for the assembly language operand. If the address in the parentheses is under hex 100 or decimal 256, it is zero-page indirect. Otherwise, it is absolute indirect. The 65C02 introduced zero-page indirect to several instructions, as that mode was not available for any instructions on the original 6502. Absolute indirect is only available for one instruction, JMP, or jump, which does not support zero-page indirect, even on the 65C02. An indirect jump is useful when you have a jump table at a fixed location where the target addresses stored there are subject to change. We'll get into that more in a later episode. Quite often, when you have an array of addresses, it's a good idea to put it on the zero page, where you can have the ability to index into it quickly using a special addressing mode called zero-page indexed indirect. This mode requires you to use the X register to provide an offset, generally in multiples of 2, into one of these arrays. Then this instruction will make the processor add the value in X to the 0-page address in the operand, and then access the data from the address stored there. It's a bit tricky to explain, but we will see a concrete example of this later. The one case where you need to have an array of addresses outside the 0 page is for a jump table. The jump instruction alone can use the absolute index indirect mode, and you can't use the 0-page index indirect mode for a jump, but otherwise, the two modes work and look the same in assembly code, but with the absolute indexed indirect mode using a 2-byte operand in machine code. This mode is introduced for the 65C02 and is very handy, but unfortunately it's not available for earlier 6502 processors. While the last two modes required you to use X, there is another that requires you to use Y, and is actually used more often. The 0-page indirect indexed with Y mode, now that's a mouthful, is the only means available for storing the base address of an array in memory at another location, and then index into it or iterate through it, in the manner in which the direct indexed modes work with a hard-coded base address. For this mode, you only have to have a single 16-bit address stored in the 2 contiguous bytes of the 0 page. The processor will then add the value in Y to the address it finds there, and use that to access the requested data. Obviously, it would be faster to use an absolute indexed mode if your code is always going to be indexing into the same array. But if your code is generic enough to work with different arrays in memory, this is your best option to have more compact and reusable code. This can also be a bit hard to understand, so we will see a concrete example of this later as well. Finally, there is the relative addressing mode, also known as the mode we won't be dealing with in this episode. This mode is only used for branching, and we will be covering that another time. In a nutshell, it uses a single byte signed operand that provides an offset relative to the current program counter. This means that, as it is using an 8-bit offset, it is limited to a range of -128 to +127, which means that branches need to be to relatively nearby locations. We'll go into this in depth in the branching episode. For now, let's create a program that uses all the rest of these varied addressing modes. It won't be a terribly useful program, other than for educational purposes. Let's open up our editor VS Codium to walk through the code. Again, at the top, we have the boilerplate to set the starting address and define the once segment. Before we get into coding any instructions, we need to set up how our data is going to be structured. First is the 0 page, where we have to have both addresses and regular data to be stored. The easiest way we have to do this is to define a few constants for our 0-page addresses. For the CA65 assembler, this is done using a name followed by an equals sign followed by a numerical expression. For these constants, we are just going to use simple numbers. For the 0-page addresses, we want to make sure we aren't stepping on anything reserved for other uses, so we will start with hex 30. This is because the X16 uses the first byte in the 0 page, address 0, for RAM bank switching, then the byte at address 1 is for ROM bank switching. The next 32 bytes are used by the kernel as a sort of 16-bit interface that we will look at in another episode. So the real user space in the 0 page starts at hex 22 and only goes up to hex 7F. Hex 80 and above is also used by the basic interpreter and the kernel for internal purposes. So less than half is available for your program to use safely. To have a nice round number to start with, we are using hex 30. Here we are going to store a 2-entry address table with a ZP pointer 1 pointing to the first entry and ZP pointer 2 pointing to the second at hex 32. Then we are going to have a little data array starting at hex 34, which we are calling ZP data. The rest of the data will be sitting alongside our code in the main part of RAM. We can prevent the processor from trying to interpret data as instructions by jumping over it. You may remember in the previous episode, we created a label called start at the beginning of our code. We are going to keep that in our new program, but instead at the very beginning of the program's memory, it's just going to be at the beginning of our executable code. This time, at the beginning, we will only have a single instruction, jump start. This means that when the program is run, it will immediately jump to the code with the start label, skipping the data block we are defining immediately below. Even though we don't see a number in this jump instruction, this will be using the absolute addressing mode for jump, and the assembler will automatically calculate the address of start, and use that as the operand in the machine code. This way, we don't have to hardcode addresses in our assembly. If something has an address within your code, you want to make use of labels rather than trying to calculate what those addresses are going to be. Let the assembler do that work. If you need to access something outside your code, like a zero-page location or something in the ROM or in banked RAM, then you want to use constants to define those addresses, as those are subject to change. You will also notice a semicolon after the instruction, followed by the word absolute. This is a comment, and it is ignored by the CA65 assembler. I'm going to be placing comments after each instruction to name the addressing mode that is being used. You can use comments however you like in your code, or even not at all if you want to be mysterious. So between the jump instruction and the start label, we are going to define some data with initial values. We do this in CA65 with control commands like .byte, which reserves space for a byte of data with an initial value that will be placed in our program file. This way, when our program is loaded, these initial data values will also be loaded. You can define multiple bytes in a row by having a comma-separated list of initial values, like we see here. Our first .byte command has 8 hex values, so these 8 bytes will be placed in our program file right after the jump instruction. You can also see that we precede these 8 bytes with a label creatively named data. This will give us an address to use later on in the code. It effectively defines an array of 8 bytes named data, and we will see how we can index into it using some of the addressing modes we saw earlier. Then we have another array that we have labeled results, but as you can see, this contains only 3 bytes, and they are all 0 now. This is where we are going to store, you guessed it, the results of our program. Like we did in the last episode, we can use the emulator's debugger to see if we successfully wrote the correct values to RAM. When we run on an actual hardware, we can use the printp command again, but this time we would need to look at the program listing to see at what address the assembler placed the results array. Now that we have this data block defined, we are ready to start our code at the start label. What we want to do first is to copy some bytes from the data array to the ZP data array on the 0 page. As we know that our program starts at hex 080D, anything we put in there, instructions or data, will not be on the 0 page. All of it will require absolute addressing. So moving some of the data to the 0 page along with some of the addresses of that data will help us make some faster running code by taking advantage of the addressing modes that use the 0 page. Let's start with the simplest way to copy data, with an LDA using the absolute addressing mode to load the first byte in the data array into A, so that now both have the value of hex 01. Then we store it into the beginning of the ZP data with an STA using the 0 page mode. After that, we move on to the next byte. This time we are going to use indexing to get the data we need. First, we use LDX with the immediate mode to load indexed register X with the value 1. Then we use LDA with the absolute indexed with X mode to put the next byte from data into A, followed by an STA with the 0 page index with X mode to copy it to the next byte in ZP data, so that now the first 2 bytes of both arrays match with the hex values 0, 1 and 2, 3. For copying the third byte, we are going to switch to using Y for our index. That means we need to have the value of 2 loaded into Y. But rather than doing that directly with an immediate LDY instruction, we are going to use 3 instructions using the implied address mode to do it. First, we use the TXA instruction to transfer the value from the X register into A, which we know is still 1. Then we transfer that value to the Y register with the TAY instruction. Unfortunately, there is no such instruction as TXY to transfer directly between the index registers. You're going to have to use either the accumulator, as we did here, or RAM as a go-between. Finally, we use the INY instruction to increment the value in Y, so now it's finally 2. Now, just as we did with the last byte, we are going to use the index modes to copy the third byte, which is hex 45, but with the modes using Y. Of course, none of this was efficient. We should have stuck with just one index register and did this in a loop, but this was just to show you how to do it using all 8 of these addressing modes. Besides, looping and branching is going to be in a later episode. The important thing to note is that even though we use the LDA and STA mnemonics 3 times each for these instructions, each instance is going to use a unique opcode because they all have different addressing modes. Now we want to set up the address table on the 0 page. First, let's set ZP pointer 1 to the address of the data array. This being the 6502, we have to do that 1 byte at a time. We already used the data label to get the absolute address, but we can also use it to get an immediate value that we can copy. We also want the low byte of that address to come first, so we can use the less than symbol to tell CA65 to use the lower byte of the address of data. The hash before that denotes immediate mode, of course, and after this first LDA instruction, A will have the lower byte, which we then store at ZP pointer 1. Now we want the high byte of that address to go into the next location in the 0 page, which would be hex 31. We don't want to hardcode that address either, so we can use a calculated address for that. We simply tell the assembler to add 1 to the constant ZP pointer 1 and use that as the 0 page address for the STA instruction. Of course, before that, we need to load A with that high byte of the address, which we can get by using the greater than symbol. If we simply try to do an immediate load of data without the less than or greater than symbol, just hash data, the assembler would report an error as you would be trying to use a value greater than hex FF or decimal 255 as an immediate value, and that just wouldn't fit in a single byte. Then we set up ZP pointer 2 in a similar way to get an offset of 4 bytes into the data array. We do this with an arithmetic expression, just like when we had a +1 for a 0 page address above, but this time with an immediate value that is also part of a 16-bit address. So we use the data +4 expression to calculate the address we want, then place it in parentheses after the less than symbol to get the lower byte of that calculated address. Now we load this into A as an immediate value that we let the assembler calculate for us. We store that lower byte at ZP pointer 2, and then do another load store pair to get the high byte of the address. Now we have 2 addresses stored contiguously in 4 bytes on the 0 page. Now we are going to use this 0 page address table to access the data array indirectly. We can access the first byte with a simple indirect load of ZP pointer 1 with no indexing. Then we store it in the first byte of the results array with a simple absolute address. Rather than using an indirect load of ZP pointer 2, we increment X to make it 2, then use that as an index into the 0 page address table, letting the processor add the value of X, which is 2, to the address of ZP pointer 1, which is hex 30, and then use that address, 32 or ZP pointer 2, to do an indirect load. This should load A with the 5th byte in the array, which is hex 89, and store that into the second byte in the results array by calculating that address with a simple +1. Next we go back to using the address at ZP pointer 1, but then indexing that with Y, which also has the value of 2 now. This means that doing an indirect load indexed with Y will retrieve the 3rd byte in the data array, which is hex 45, which we then store in the 3rd byte of the results array with an absolute index with Y, using the same index register for both arrays. So now we have the first 3 bytes of the data array copied into the 0 page starting at ZP data, and the first, 5th, and 3rd bytes in that order copied into the results array. Like I said earlier, we can verify this easily with the emulator's built-in debugger. Okay, we've dealt with the modes we use to move data around, so all we have left are the addressing modes we use for changing the flow of a program. That is jumping and branching. As we are going to deal with branching in another video, we're going to do examples of the 2 modes that are only used for jumping to absolute addresses. We've already seen the regular absolute mode for jumping when we did the jump start instruction at the beginning of the program. When we know the address we are always going to jump to, that's the appropriate mode to use. But if we want to be able to programmatically determine where we are jumping, we can use one of the absolute indirect modes. First, we are going to do a simple absolute indirect jump by storing our intended destination labeled lookup at a location labeled lookup pointer. Then we use that stored pointer by placing lookup pointer inside parentheses after the jump mnemonic. This will make the processor fetch the address of lookup from lookup pointer and then jump there. As you can see, we placed lookup after lookup pointer in our program, so we can have something non-executable in the middle of our executable code, and that's okay as long as we're jumping over it. At another point in our program, we could place a different address at lookup pointer if we wanted to jump somewhere else when we execute the code again, or do another indirect jump using it. Now at lookup, we have another jump instruction, but this time it is using the absolute indexed indirect mode, which will add the value of x to the address we placed in the operand. Since x is currently 2, we need to make sure that the address we are using has a valid executable address 2 bytes past it. We do this by creating a jump table in line with the code with the creative label jump table. For this, we use the .addr control command to place 2 addresses in contiguous RAM. Since we know we are going to skip over the first one, we put start there, which we could use to run the program again from the beginning if we wanted to use this jump table again. But as x is 2, it's the next address that is going to be jumped to, so we place the return label there. So now, when we execute that indexed indirect jump with x being 2, the processor will fetch the address for return from jump table and put that in the program counter, and our execution will continue at the return label right below jump table. As you can see, all we have there is an RTS instruction, which means we are going to return back to the basic interpreter and our program is done. Now let's go ahead and build it. This time I have made a build script to speed this up, which we can see right here. We are going to call the PRG file memory.prg. While it would be awesome to have a demo that plays music from cats, this is just going to be moving data around RAM. Now in our workplace, we can cd into the lesson 2 directory and just run build.sh. Still pretty quick. Let's take a look at what we got with a quick ls. We see the memory.prg that we are going to load into the emulator and a new machine code listing in memory.list. If we take a look at the listing, we can see all the machine code that we expected and that our results array is placed at hex 818. This will be helpful when we go to verify our program in the emulator debugger. So let's get right to it and start the emulator with the -debug option. Let's load our program into RAM with the load memory.prg. Now, if we open the debugger by hitting F12, we can take a look at the state of RAM before we run. Right away, we can see that the 0-page RAM after the bank registers is all zeros through hex 80, which begins the part reserved for the basic interpreter and the kernel. If we take a look at the results array address with an M818, we can see 3 zeros there as well, just as we initialize them in our code. Now to run it, we hit F5 to get out of the debugger and just type run. Just like last time, this is pretty anticlimactic. All the stuff that this program did was under the hood and can only be seen by peeking into RAM. So let's do that again with the debugger. We already had the memory window set up at the start of the results array. We can immediately see our results array has been populated with hex 018945 as we expected. We can then go back to the 0 page starting at hex 30 by typing in M30. And now we see the 2 addresses we put there, followed by the first 3 bytes of the data array, hex 01, 23, and 45. With the data all sorted, let's take a look at the program flow. We can run the program again, but this time we are going to set a breakpoint at the beginning. This will cause the emulator to pause when the program counter reaches the breakpoint, which we will be setting to hex 80D, which you'll remember is where we set up the machine language portion of the program to start. To set the breakpoint, first we need to set the disassembly window to start at the desired address, which we can do by typing D80D. Now we can see that first jump instruction right at the top, but under that we see some completely unfamiliar code. Well, that's because it's not code, it's the data we set up there. But the debugger doesn't know it's not code, so it tries to disassemble it anyway. We can see the next real instruction down at hex 81B, which is good because, as you can see, that's the address that the initial jump is targeting. Anyway, let's set that breakpoint by hitting F9. Now you will see to the right the address next to break is 080D, so we know that it's properly set. You will notice above that all the current registered values are displayed, which is nice to have while you are debugging. Let's exit out of the debugger by hitting F5 and run the program again. As you can see, it immediately stops and the debugger pops up automatically as the program counter has now hit 080D, as evidenced by both the instruction at the top of the disassembly window and the value next to PC on the right. To step to the next instruction, we hit F11. Yep, we jumped right ahead to hex 81B, which is start. If we went back to the machine code listing, we could verify that. Now we know this first part of the program is working, so we're going to keep stepping until we get to the next jump. Okay, now that we're there, we can see that the simple indirect jump is going to fetch its target address from hex 0853. Let's go ahead and take a look at that in RAM by typing M853. So here we can see the little endian address 0855, with the bytes switched as expected. Now when we hit F11 one more time, we see that we jump right to 855. Now we're ready to do the next jump, which will be an indexed indirect one using hex 858 as the base address of the jump table. Let's shift the memory view by typing M858 so that we can see the jump table right at the beginning. Now we can see two little endian addresses in a row, hex 081B, which you may remember is a start address that we jumped to at the beginning of the program, followed by 085C. As we can also see in the register display, the current value of X is 2. So we should jump to 85C for the next instruction. One more F11, and there we are, 85C, which has our RTS instruction, meaning our program is done. We'll go ahead and let it finish by hitting F5. And now we're back to the basic prompt again, and our program is done. Now let's try this on the real Commander X16. After we copy memory.prg to an SD card, we can put it in an X16 and start it up. Then, like in the emulator, we load it and run it. Before, we printed memory locations using peek, which we can do with the first byte of our 0 page data at hex 34. As expected, it's 1. For other bytes, we are looking for hex values 2, 3, and 4, 5, so we don't want to print out them as decimal one at a time. Luckily, the X16 has the machine code monitor, which we can enter with the command MON. Here we see the current register values, starting with the program counter. It's way up in page E4, which is in the ROM. That makes sense, as we went into the monitor from the basic interpreter. Next, we see the RAM and ROM bank registers. RAM Bank 1 is the first bank that is free for basic programs to use, so that's what's currently selected, rather than Bank 0, which is used by the kernel and could cause some serious problems if a basic program wrote to it. Next, the ROM bank is set to 4, which is the bank containing the basic interpreter code, so we're definitely in the middle of executing that. Then we see the current values in the accumulator, the X register and the Y register, which would mean something to someone familiar with this particular location in the basic code, but that's not me. Then we see the stack pointer is at F6, which means we are up to 5 addresses deep right now. To take a look at 8 bytes of memory at a time, we can use the M command, followed by a space, and then a full 4-digit hex address. So we want 0034. Then hit enter. Now we can see all 3 bytes of our 0 page array at once, and it's 0, 1, 2, 3, and 4, 5 like we expected. Now let's take a look at our inline results array, which you may remember is at address 818. First we hit enter a couple times to get back to the period prompt, then enter M space 0818. Now we can see 018945 like we expected for here. And that's all we got for this lesson. I hope you learned a bit about how all these addressing modes worked. If I went through it a bit fast for you, please go ahead and check out the slides and the script of this video right in the GitHub repo linked below. The code and all the materials will be in the Lesson 2 subdirectory. I also hope that you check out the next episode in this series, and the best way to make sure you don't miss it is to first subscribe to my channel, and then click on that bell to receive notifications for all my video premieres. If you want to support my channel further, you can click the join button to become a channel member, or join our Patreon community like the folks you see here. Either way, you will have ad-free access to all my videos before they are available for the general public. Thanks for making it this far, and I hope you come back soon. Bye-bye.